Okay, let's get started. So, so we're continuing on with our sort of explication of definitions of points of topology. So more points of topology. And you remember the last thing that we did was we showed that we showed this theorem that a set is open if and only if the complement is closed. Okay, right. That's what we finished up with. And so we're going to start off today with sort of combining this theorem with so-called DeMorgan's laws of sets. Anybody familiar? Is anybody familiar with DeMorgan's laws? It's Huang. Do you want to say what it says?
Yeah, I'm not 100% sure if it's comprehensive, but I believe not all is like for example A or B is equal to not like it does not change the sign. Basically, I think.
Maybe you're thinking about something, but on something different.
Yeah, we are wrong. We are wrong. Yeah.
So DeMorgan's laws has to do with complements and intersections, basically. Complements, intersections, and unions.
Yeah.
So it will basically. It's like this. You have an infinite. You have some sort of collection of sets, maybe finite or infinite. And what it says is that if you take the complement of the union is the same thing as the intersection of the complements. Same. Right. So like you have a bunch of sets. You have a bunch of sets, and then you take the union, and then you take the complement of that. That's the same thing as if you took the sets themselves and complemented them and intersected those complements, right? So it's this sort of thing. So the complement of the union is the intersection of the complements. It's this sort of thing. So yeah. So yeah, I'm not gonna prove that. That's pretty straightforward. But what we are gonna do is use it to show some facts about open and closed sets, and unions and intersections. Okay. So the first one is that if you have a collection of open sets, then the union of them is still open. Okay, so any union of open sets is still going to be an open set. The second one, if you have a collection of closed sets, then their intersection is closed. Right. So even if it's an infinite intersection. Okay. Third one is that if you have a finite collection, so G1 to Gn, a finite collection of open sets, then its intersection is still open. And the last one, that if you have a finite collection of closed sets, then the union is closed. Okay. So infinite, finite, any sort of union of open sets is still open. any sort of intersection of closed sets is closed. A finite intersection of open sets is open. A finite union of closed sets is closed. Okay. And in these last two, the finiteness is really important. So, like, can anyone think of an infinite collection of open sets whose intersection is no longer open? Anyone come up with an example of something like that? You've got a bunch of open sets. You can come up with one in, say, in R, just in R.
Probably infinity to 1 and then
Infinity to?
to 1 and then negative 1 to infinity. Like negative infinity to 1.
Infinity to 1.
No,
So
yeah, negative infinity to 1 and then 1.
negative infinity to 1.
1.
Okay.
And like negative 1 to infinity.
Negative 1 to infinity.
Yeah.
Okay. Okay, but what
We can inclusive one.
Say it again.
We can like make 1 and negative 1 inclusive, like.
Okay, but that's in that case, that's not an open set anymore, right? That's a closed set now.
Oh.
So yeah, so no, no. Here's an example. What you can do is take, like, say, 1 over n, comma 1 over n. The sets like this: 1 over n. Sorry, negative 1 over n, 1 over n. Right. So negative 1 to 1, negative 1/2 to 1/2. Right. Negative 1/3 to 1/3, etc., etc. Then when you take the infinite intersection, what do you get?
A point?
You get a point, right? Just 0 is going to lie in all of their sets. Sorry, I've got some dust in my contacts. I'm not crying. Give me 1 second. Sorry.
Tea or water? Actually, water. Just want to go out.
Sorry. Okay, right. So, right, when you take the infinite intersection, you see that it's not open anymore, right? The infinite intersection is just going to be, the set of this single point, which is a closed set. Okay. Well, before running out, I should have said I want you to just do this by yourselves. So see if you can prove the first one. If you have a collection of open sets, then the union is open. Take a minute and see if you can prove it. And I'll walk outside. And feel free to talk to each other, of course. Yeah. Okay, anybody get it? Anybody get it? And you look like you have something?
I have,
Yeah.
would we
Yeah.
try to prove that any element is an interior point?
Yeah, right, so for one, right, we want to show that any x in the union, any x in the union is interior, right? In other words, that you can find a neighborhood around x that's still contained in here, right? Okay, so how would we find that? You can sort of think like you have some G1, you have some G2, right? You have some G3, you have some G4, right? And you're trying to show that the union is still open, right? Right? How would you choose any point in here? Choose any point in here. How do you show that that point's interior to the union? You just need to find a neighborhood around it that's contained in the union, right? So how do you find that neighborhood? How do you know that such a neighborhood exists? Natalie, you're smiling?
Well, we know that neighborhood exists in in at least one of the components of the
Exactly,
union.
exactly, right? We know that this guy is going to lie in one of these sets, and each of these sets is open. So you've got the neighborhood for that set, and certainly then you've got the neighborhood for the union, right? Okay, so yeah, exactly. So this is sort of like, are you getting the definitions, right? So here, want to show anybody's interior, right? So we know x being in this thing means that x lies in some g alpha naught, right? For some alpha naught in the list of indices, right? G alpha naught is open by hypothesis, right? So, right, there exists some neighborhood around the point that's contained in G alpha naught. Right? Is it clear? Okay, right? But, of course, G alpha naught lies inside of the union of the G alphas, right? So we found a neighborhood around X that lies inside of the G alphas, inside of the total set, right? So X is interior to the union, right? X is definitely interior to G alpha naught, right? Because G alpha naught is an open set, and X lies in there. And since G alpha naught lies inside of here, then we're done. Okay. Okay. So okay. Okay. Part 2, showing that any intersection of closed sets, is still closed. Anybody know how to do that? Anne.
Would it be kind of the same logic, but proving that every point is a limit point?
You could do it that way. So that's definitely one possible way. You would say, look, it's a little bit tricky, I think, but you could do it that way. But actually, a more straightforward way is to use the previous theorem. So to show, right, we want to show that the intersection of these closed sets is closed. But that's the same thing as saying that the complement is open, right? By the previous theorem, right, the complement has to be open, okay? But the complement of the intersection, right, I can rewrite this as, let me rewrite this as like this. Let me take, I'm going to take complements of everything here. So this is going to be FA complement equals that. You see, I'm just writing, I'm taking the complement of the set here. Over here, I'm going to get the complement of the complement, which is just the original set, right? So I get the complement, well, and then I'm going to move the complement to the other side. Okay, take complements of both sides. So the union of the complements equals the complement of the intersection. Okay, so we want to show that this thing is open, right? We want to show that the complement of the intersection is open. Well, by DeMorgan's other law, we know that that's the same thing as showing that the union of FA complement is open, right? Well, what do we know about FA complement? About the FA complements? The F's are and
They're closed.
F's are closed, right? So then you take the complement of those guys, they're open, right? So we've got a union of open sets. A union of open sets by part one is always going to be open, right? So by part one, part A, you're done. Okay. How are you guys doing? Are you okay? Is this all right? Okay. 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 Good. Okay. I hope this is I hope this is all right. Ask questions if it's not. Okay. So 1 and 2 are the same, and the spoiler is that C and D are also the same, via DeMorgan's laws. So let's prove. Okay, I'm gonna erase this. I'm gonna erase this now because I want to keep that up. Is that all right?
Yeah.
Yeah. I'll just erase the top part. Wish I had more boards. Okay, so let's prove C, that a finite collection, if you have a finite collection of open sets, then their intersection is always open. Okay, so we want to show that that the intersection of these open sets, right, from I equals 1 to n is still open. Okay, now think about that, right? We want to show that if we've got a bunch of open sets, right, let's just take 2, right, then the intersection is still going to be open. Okay, well, we have to show that we can find we can find right, given any point in the intersection, that we can find a neighborhood around it that is contained in the intersection. Okay, how are we gonna? So, anybody see how we're gonna get it? We want to find a neighborhood that's contained in the intersection. Right? What do we have? Each of these sets is open, right? This is open, right? So this guy, it lies in this open set. What does that give us? Charlotte, you twitching?
Oh, just I guess that it already has, like we know that X has a neighborhood around it.
For G1.
For G1,
yeah,
'cause
for
it's
G1.
open.
Yeah, so we've got a neighborhood around it for G1, right? Let me draw the sets a little bit more crazily. So this is G1 and this is G2, right? And here's X. Okay. So we've got a neighborhood for G1, right? Great. But as you see, that doesn't lie in the intersection. Okay, and then we've got a neighborhood for G2, right? So there's another neighborhood for G2, right? So how do we get a neighborhood that lies in the intersection? Just
Take like the minimum R.
right, take the minimum R. And we can do that because there's finitely many, right? If we had an infinitely many, then that minimum would become an infimum and might turn into 0, right? But if it's just a finite number of things, each of those is a positive number, there's going to be some smallest positive number, right? So that's the idea, right? So you say, we want to show this is open. In other words, that given any x in the union, there exists a neighborhood around it that's still contained, I'm sorry, in the intersection, there exists a neighborhood that still exists, that lies in the intersection. Okay, and so what do? You say, well, this guy lies in every single every single one of these sets, right? So X lies in GI, each of which is open. Each of which is open. So we know that there exists some neighborhood R sub I that's contained in G sub I. Right? There's a neighborhood of X with some radius contained in G sub I. Right? So then, if you take the neighborhood with the minimum of the R sub I's, right? That will lies in every G sub I, right? Right, so lies in G sub I for each I. Right, in other words, it lies, i.e., this thing lies in the intersection. And we're going to show it.
How do we know that there's a limit point in the intersection? Because couldn't they still, like, the two sets could intersect and the intersection could not be empty, but that doesn't guarantee that there's a limit point in them?
We don't need to guarantee a limit point. Wait. Why do you want a limit point?
Well, because, I mean, the definition for closed and open sets relies on, like, whether a limit point is, is in E, or like it relies on the limit point.
Right now we're just talking about open sets though. So open sets is not a statement about limit points. It's just, if you're interior or not.
But that's if the limit points are interior.
No, it just means that every point in the set is interior.
Okay.
Every point in the set is interior. It may not have any limit points. Yeah, I can't think of a good example, but yeah, it need not have limit points. Yeah, but what we want to show is that every point in the set is interior, right? In other words, that every point in the set has a neighborhood around it that's contained in the set. That's all we need to show.
Got it. Okay.
Yeah. Okay. Right. Right. This statement is about limit points. Right. This one is about limit points. It says you have to show that the set contains all its limit points. Right. But we kind of get around that by just using DeMorgan's laws on it and referring back to this one, using the complement one.
Okay.
Okay. Yeah. Yeah. So this with this statement, we don't need to say anything about limit points. Okay. 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 Go on. Yeah, the only example I can think of offhand of an open set without any limit points. Can anyone think of an open set without any limit points? The only one I can think of offhand is using the discrete topology. So you remember we made this funny metric where you have distance of 1 if x is not equal to y, and distance of 0 if x equals y. Right? This was a metric, right, that we called the discrete metric. Right? What are the neighborhoods in this case? What's a neighborhood? What's a neighborhood? So suppose I've got a bunch of points here, and I say I'm going to put the discrete topology on it. So I put the discrete topology on the class. What's a neighborhood? What's a neighborhood of radius 1/2, say? It'd be everything within half a distance of n, say. So what would that be? Natalie?
It'd just be
It would just be n, right? So and what about the neighborhood of radius 2?
It'd be everyone?
It would be everyone, right? So in the discrete topology, the neighborhoods are just the single points, right? Just the single points and the entire space. Okay, so it's kind of a funny one. So what does that mean? That means that that this single point here is an open set, right? This is an open set because I can find a neighborhood around it, namely itself, right? I can find the it always has the neighborhood of 1/2, right? If I look at the set consisting of this one point, well, it's interior to itself, right? Because the neighborhood of 1/2 is contained in this set. The neighborhood of 1/2 is that point itself anyway. So that's an open set. So every singleton is actually an open set. Okay. So what does that mean? It means basically that every set is an open set in the discrete topology, right? Every set, if I take, like whatever bunch of points, well, that's going to be a union of open sets, right? Because each single point is an open set, and we just said that any union of open sets is open, right? So any set is an open set in this case. But that means that the complement of any set is always open. So every set is closed also. So every set in this topology, which is kind of a weird one, everything is closed and everything is open. Okay. And this is an example of a set where you can have open sets that aren't limit points, right? Because here, right, in this example on the board here, there's no limit points, right? Nothing is a limit point here, but it's all open. Okay. Don't worry. It will all become natural eventually. Okay. Yeah. It's strange. It's strange at the beginning. Okay. Don't worry. Okay. Next thing, important idea. Closure. Wow. The closure of a set. So remember what I said, we introduced this notation. So we have this notation that E prime is the limit points of E. Okay. And we introduce another notation, the closure. So E bar is defined to be E union E prime. Okay, so you take the set and you throw in all the limit points. Okay, so simple example, right? We have 0, 1, right? 0, 1. The closure of 0, 1 is going to be the closed set, right? Because you throw in the limit points, right? If I have an open ball and I close it, right? If I have an open ball and I close it, right? Then that's going to be the ball, but also containing the boundary. Would be the ball with the boundary on it. Okay. So so let's just do it here. Out of space, I think. Okay. So theorem about closure and closedness. First, that E bar is a closed set. Second, that a set is closed if and only if E equals E bar. Third, that if you have E contained in F, which is contained in your metric space, if F is closed, then E bar is contained in F. Okay, so if F is closed already, then when you close E, it's still contained in that set because the set was closed already. Okay, so Okay, so this is not too bad. Okay, so proof of A, right? We want to show that E bar is closed. Well, let's show that E bar complement is open. Okay, so remember, so E bar is E union E prime. Okay, so let's choose something that's not in E, and it's also something that's not in E, and something that's not in E prime. Okay, so let X be in the complement of E bar, right? So it's not a limit point of E, right? In particular, X is not a limit point, right? X is not a limit point of E, right? What do we know if you're not a limit point? Well, that means that there's some punctured neighborhood that doesn't intersect E, right? That's what being not being a limit point means, right? So there exists a punctured neighborhood, right? A punctured neighborhood around X, right? That doesn't intersect E. That does not intersect E. Right? So far so good. Right? Doesn't intersect E, right? But X itself is not in E, so I can say that the whole neighborhood doesn't intersect E, right? Not just the punctured neighborhood, right? X, the center, also doesn't intersect E. Right. Okay, so we have an entire neighborhood that doesn't intersect E. So here's my X, and we know that E lies outside there. Okay, okay. So right, but then let's take a neighborhood of half the radius. Okay, let's take a neighborhood of half the radius. There also exists this n0 over 2, right, that does not intersect E prime, right? There's no limit points definitely can't be any limit points inside, there can't be any limit points of E inside here, right? Because this whole space here, right? This whole stuff here is in E complement, right? So what do we have, right? So the smaller of the two intersects neither E nor E prime, right? Right. The bigger one doesn't intersect E. The smaller one doesn't intersect E prime. Certainly the smaller one intersects neither E nor E prime, right? And so, the smaller one is contained in the complement of E union E prime, right? Which is E bar prime, E bar complement, right? Equals E bar complement. And that's what we wanted to show, right? We wanted to show that E bar complement was open. So we've shown that any point in E bar complement is interior to E bar complement. Okay. 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 Okay, second part is a proof of B. Right? We want to show that E being closed means that E equals its closure, right? So right. right? So the first thing we showed was that E closure is the closed set. Okay. We want to show that E being closed means that E equals E closure. So what about going in this direction? Suppose we know E equals E closure. Does that tell us that E is closed? Yes, right? Because we just said E bar is closed, right? If E equals E closure, E is a closed set, right? This is closed, so we're done. Okay, so going backwards is easy, right? Going forwards, right? Suppose we know that E is closed already. Say that E is closed already, right? And we want to show, right? We want to show that E equals E union, right? E equals E bar. In other words, E equals E union its limit points. Okay. Anybody see why that's also like a straight shot? Write down. Take 10 seconds and write down something. Why is that definitely going to be true? Definitely true. Okay, anybody want to tell me why that immediately follows? If you're closed, then go ahead, Charlie.
Then the set contains all of its limit points.
Exactly, right? That's the same thing as saying that E contains E prime, right? So, right, so E prime is contained inside of E to begin with, so, you know, E definitely equals E union E prime. Right? So that's okay. Good. Okay. Last one, proof of C. Right. Suppose you have a set E and it's contained inside of a closed set. Incidentally, people use F for closed because of the French word fermé, which means closed. Okay. Yeah. So suppose E is contained inside some sort of closed set. Show that the closure of E is already contained inside of F. Okay. Let me just do this one for the sake of time. You say, well, right, we want to show that E bar, which is E union E prime, is contained inside of F. Right? That's what we want to show, right? That the closure is contained inside of F. Right? We already know that E is contained inside of F. Right? So the only thing we have to show is that E prime is contained inside of F. Okay. So suffices to show that E prime is contained in F. Okay. Once we do that, we're fine, because E is already in there. Okay. Right. But what you notice is that since E is contained in F, the limit points of E are limit points of F. Right? Limit points of E means that you've got, you know, all your punctured neighborhoods intersect E, but E is part of F, right? So that would make you a limit point of F as well, right? If you're a limit point of E, you're also a limit point of F, right? Okay, and F prime is contained in F, right? Right, because this is F bar, but F bar is F. Right. The limit points of F are contained in the closure of F, but F is closed already. So F bar is F, right? So what do we got? That E prime is contained in F. Okay. So okay. So yeah. So Okay. The implication of this last statement is that E bar is the smallest closed set that contains E. Okay. So remark, thus E bar, the closure of E is the smallest closed set containing E. Right, so like when you have, you know, right, like you have any, if you have any closed set that contains E, well, E bar is contained inside that closed set. Right, given any closed set containing E, E bar is contained inside that set. Right, so you've got, you know, either E bar is F or E bar is some smaller set than F. So it's the smallest closed set containing E. And that actually gives another way of defining E bar, which is you take all closed sets containing E and you intersect them all. And that turns out to be E closure. Okay, the intersection of all closed sets containing E will turn out to be the closure of E. I think that might be an exercise in the homework. Okay. 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 Okay, let me start. So I'm going to skip an idea, but I'm going to come back to it. The idea of relative openness. Okay. So let me get back to it next time. Let me, instead of doing that, let me get into the main idea that I hope to get to this time, which is that of compact sets. So this is a super, super important idea, but it's really, it's kind of hard to get your head around. Okay. So here's the definition. Okay. So you have X, the metric space, okay. And you have some set contained in X. Okay. So first we need sort of a transitional definition. So any collection of open sets, G sub alpha, such that E is contained in the union of the G sub alpha, is called an open cover. Of E. Okay, so like if I have some set in space E, and then I have a bunch of open sets, right? I have a bunch of open sets, and their union covers it. Then that's called an open cover of E. Okay, that's a pretty natural definition. Okay. Okay. The definition of compactness is kind of a kooky one. Here it is. So suppose you have some K in X, and it has this property. So if K has the property that given any open cover, there exists a subcollection G alpha 1 through G alpha n. That is still an open cover. There exists a finite subcollection that is still an open cover. Okay. Then we say K is compact. So this is a weird one. It says that no matter what open cover you're given, there's going to be a finite subcollection that's still an open cover. Okay. So let's do some examples. First example, a singleton. Let's say that we're in Rn, in Rn. You take a single point, okay? That's definitely compact, right? So you've got the single point in space. You've got a set consisting of a single point, and you notice that if I have any infinite, any cover, right? Right. So I've got a bunch of sets, and their union covers this set. I can certainly find a subcollection that still covers it, right? I just say, one of these sets has to cover it. Let's call that one G sub 1. Then, right? So I start off with, infinitely many guys, infinitely many sets. But I can definitely find one that covers it because we know that this union covers the set, right? So any singleton is going to be a compact set, right? Similarly, any finite set is going to be a compact set, right? So if I had multiple points, x1, x2, x3, say, right? Then if I've got a cover of that set, well, I know there's got to be one set that covers this one. There's got to be one set that covers this one. There's got to be one set that covers this one. And so I've got, again, a finite subcover. Is it making sense so far? Okay, great. Okay. What about if I'm in R and I look at, say, the integers? Is that a compact set? Okay. The answer is no. This is not a compact set. Why? Well, so to be a compact set means that you have the property that no matter what open cover you're given, there's going to be a finite subcover. Okay? No matter what open cover you're given, there's going to be a finite subcover. So to be non-compact means that you can find a bad open cover. Okay, an open cover for which there is no finite subcover. Okay, so I'm going to make one. Right, here it is. I'm going to cover each of these guys with a tiny open interval. Right. Okay, I'm going to call the intervals I0, I1, I2, et cetera, right? Then certainly the union of the i's covers my set, right? The union of the i's covers my set, but there is no finite subcollection of them that still covers the set, right? Because if I take a finite subcollection of them, well, I'm only going to hit finitely many integers, and there are infinitely many integers. Is it making sense? Right? So as long as I can find a single bad cover, then I know my set's not compact. Okay. And you might say, but you can find a cover you can find something that finitely covers the set. That doesn't matter. Right? As long as you can find one bad cover, then the set's not compact. Okay. Okay. We better stop here. We'll start off with this next time. But this is a super crucial idea. And let me sort of say one thing, that is compactness. This is going to be mysterious, but it'll become clear. Compactness is basically like finiteness for infinite sets. Okay, it's finiteness for infinite sets. It's sort of like your infinite set has qualities of finite sets. Okay, right? Qualities. You see that for finite sets, any open cover has a finite subcover, right? And what we're going to say is that an infinite set that has similar qualities is called compact. So it's like finiteness for infinite sets. Okay, that's it for today.
I'm so glad there's sun today.
Excuse me.